Hello, in this video we're going to be talking about electric potentials, so let's not waste any of your time. Let's get right to it. Now when we're talking electric potential, we want to establish what exactly we're talking about. But what we're talking about is a difference in the charges, okay, of elements and materials inside the cell as opposed to outside the cell. When there's that difference, okay, in between positive and negative, then we're going to be able to create that gradient, which is what's going to trigger the neuron firing and to help send that signal onto the next neuron. Now, one of the things that we're going to be focused on here is that sodium-potassium pump that we looked at during Chapter 2, the chemistry section. That's going to play a big part of what we're talking about here. But we're going to be referring to a lot of different charge numbers, so it is going to be important that you make sure that you are writing down what those charge numbers are and what happens at those various stages. You're going to hear resting membrane potential, or you'll see it as RMP probably from now on. But that number is -70 in whatever that unit is. Microvolts, I'm sure. But so -70 is the number that your neuron cell sets at when non-firing or non-excited, just in its everyday normal typical self. -70 is that number, and then when the signal arrives, it goes through a series of steps to increase that number using sodium and potassium as a way to make that go up to a +35 and then back down to its resting potential. But we'll talk about all those steps in this video. Okay, so our main focus on this is going to be this sodium-potassium pump, as you can see here. And it's referred to in that way because simply there's a specific protein in the membrane that targets only sodium elements, and one that targets only potassium. So they are specific proteins only for those two elements, and they each have their own. But a general overall view, and then we'll talk about each step individually. When the nerve signal arrives, okay, that brings a little bit of energy, and these channels, one at a time, are opened, and these are just one direction only. So unis on the protein types. The one on the left is the sodium, as you can see. The one on the right is potassium. And when the sodium channel opens up, sodium elements come pouring in, okay, and they are positively charged, which is going to increase the charge level inside of the cell. And then once reaches that +35 level, then the potassium channel opens up, and potassium, which are also positive, begin to leave, which lowers it back down to that -70. Now, what makes it negative in the first place are those little green anions. They are negatively charged, so they are large molecules. They just sit in there. They can't get out, and they make it negative. That -70 number. Now this overall process happens in a kind of a two-step process. So there's a lot of steps inside of the steps, but the first thing is when the nerve signal arrives, it comes through, it connects with the dendrites from the previous neuron, and is sent through the dendrites into the soma. And when it hits the soma, that's when the local potential begins, and then that moves down the soma to the trigger zone, which is at the bottom of the soma if you're looking at it upright, and that's when it generates the action potential. And it's the action potential that moves down the axon to the next neuron. Local potentials, we're going to talk about some characteristics here a little bit, but they are smaller in scale as far as energy-wise than action potentials. But it's got to start here. It's that change when a nerve signal comes in from the previous neuron. Now, when an action potential begins, the neuron is stimulated by some kind of a signal, chemical, whatever it may be, and then as we saw that sodium-potassium pump that fires the sodium, and those sodiums come roaring in to get that increase, that voltage change, and then as it continues, then a second sodium channel opens up so it can release the sodium. So it goes up, and then it resets itself back down. And this is a look at how this is happening. So we're talking the dendrites. So we're talking to the left. If you're looking at that diagram of the soma, the signal is received, and you got the two sodium pumps, and it comes roaring in, and then when it sets back down, it goes roaring back out. Alright, so some characteristics. The words we're going to look at are graded and decremental. And when we look at action potential, we'll look at those same two words as a comparison. But local potentials are graded. In other words, they vary in magnitude, their stimulus strength, based on the importance. Some stimulus are stronger, some are weaker, and that's one way that your body recognizes importance. And we'll talk about this, I think it's in the brain chapter, when it gets a strong signal frequently, that takes greater precedence over a weak random stimulus. But they're also decremental. In other words, they decline in strength as they get farther away at the point. So the dendrites, they are stronger in strength, and by the time they get all the way down to the trigger zone, they've weakened over that distance. And continuing this, they're also reversible. Okay, they can the stimulation can cease and return. They can not only can they be excitable, as we've been talking about, they can also be inhibitory. Some neurotransmitters, and we'll get into neurotransmitters, they can inhibit a situation. In other words, stop the action. And we'll talk about the hyperpolarized. We saw that we'll see that here in a little bit, the different sections of the potential. But we'll talk about what that means. That's the last phase, I should say. All right, so now getting into the action potential, which is the major portion of sending the signal down the neuron. This is the part that starts at the bottom of the soma, the trigger zone, and generates an action potential. An action potential is the main aspect of sending that message from neuron to neuron. Okay, these are stronger stimulated parts of the, and when we look at the characteristics, it's an all or nothing, but anyway, they're much stronger, but they start at the trigger zone, which is again is that section at the bottom of the soma. All right, we're on the next slide. We'll see this, and we'll see all this stuff and how it's playing out. But this is where the sodium potassium pump really comes into shape, and that up and down shift in charges, going from that negative 70 up to the plus 35, and then back down to the negative 70. But we'll talk about each of the sections: the local potential, then the depolarization, the repolarization, hyperpolarization on the next slide. All right, so here's our look at our action potential, and you can see that in the far left of the graph, where the red line begins, it's that negative 70 number that we've been mentioning, and that's when your local potential is in action. And then as those sodium channels open up and they come roaring in with their positive aspect, they begin to increase that energy level, and then once it gets to negative 55, okay, that's the second important, well, that's the third important number with the plus 35. That's when it fires. Okay, that's when it fires, and then the potassium channel begins to open up, but those sodiums are pouring in to increase it up to plus 35, and then the potassium gate opens, and the potassiums go roaring out, and to lower it back down to that negative 70. And you can see the different names there, but the things to remember is that negative 70 is the resting membrane charge amount, and when it gets to negative 55, that's when the threshold, that's when it fires, is in that all or nothing category. So anything below that, it doesn't fire in that manner, and then again gets to plus 35, then it begins to descend back down, returning to its resting membrane potential. That's the repolarization. And of course, when it gets there and now waits for that the hyperpolarization station, then it waits for the next one. But during that phase, there are two important categories that we're going to mention here in a couple of slides. Okay, but looking again at how the sodium-potassium pump it comes into play. Step one, you can see it's at the resting membrane potential number. Okay, they're both closed. And then part two, that sodium gate will open up, sodiums come roaring in, and you can see the line going up. And then once it gets to the positive 35, the potassium gate opens up, sodium closes, and the potassiums go roaring out, and then we begin to decline in number, and then once we reach that negative 70, the potassium gate closes. Excuse me, and we're back to our resting potential. Alright, so the characteristics, especially when we want to compare that local potential and action potential. But action is all or nothing. What that means is that if it's going to fire, it fires. And if it doesn't have enough energy, then it does not fire at all. Okay. Local potentials were decremental, meaning the farther away they get, the weaker they get. Action potentials are not that way. They're the same strength all the way down the axon and to the dendrites of the next neuron. Alright, so these are the two periods of the hyperpolarization I was referring to for a few milliseconds. In other words, a very short amount of time. During that hyperpolarization phase, the neuron can't fire again. Okay, in that absolute refractory period, in other words, nothing is going to stimulate that neuron. And essentially everything is being reset. The sodium, potassiums, any resources, whatever is going on. And then in the relative refractory period, which is the yellow box, once it gets to that portion, then a strong stimulus can fire it, but that's it, super strong. And then as long as it's in a hyperpolarization stage, then it's in the refractory period at some point in time. Alright, so we've mentioned in the past that myelinated or unmyelinated affects the speed of the signal, and we're going to talk about why that is. First of all, an unmyelinated fiber, one way to protect itself, it has gates that limit or regulate the voltage. So that's going to be, if you know anything about electricity, similar to a resistor. Okay, so these voltage regulated ion gates are going to slow down the process, and it makes it to where it moves similar to how an inchworm, if you know what an inchworm is, a little caterpillar, where it reaches out and then drags the back of the body up to the front of the body, and it reaches out, so it like inches along, whereas a myelinated fiber does not do that. It speeds through the axon. So unmyelinated is like a slow process, slow, tedious process of moving, whereas a myelinated fiber is like a rabbit running, just running straight through. Speed is the most important factor. Now, because the unmyelinated fiber has these gates, and we're going to see this inch-along process, it really slows it down. But again, it just reaches out and then inches up, if you've seen it, and reaches out again. So a slow process. Whereas myelinated, just boom, zooms right through. And here is a look at this process. So this is unmyelinated, as you can see, and you can see that we've got our three parts. Got the membrane, and you got the absolute or the action potential, and then the refractory membrane. So it reaches the local potential and then the action potential, and then it just moves in a series of steps. Whereas the myelinated, it just boom, zooms right through the process. And here's what it looks like in a myelinated. Whereas you can see that instead of that inchworm type, that the mounting sheets keep that signal nice and tight in there, so it can just speed along very quickly. Well, that's our video for electric potential. When we come back next time, we're going to be talking about the synapses. We'll see you then.